So I've just turned on recording.
Yeah.
And I'm throwing up. I'm just going to stream the whole desktop. Can see things just fine.
Yep.
And I've got chat open in case anything shows up there. But today I just wanted, well, honestly, I wanted to do things a little bit slower, but seeing as we're up to using Gauss's law, I wanted to get to Gauss's law today. One moment, let me turn on my own video in case it's something people care about. I don't know what's helpful. So the idea is basically we want to look at functions, and remember last time I said functions were just mappings. So they were just a mathematical object which took inputs from some set and produced outputs in another set. Now, last time we talked about the case where the input set was still just real numbers, but the output set was vectors. And today we're sort of going to be looking at the other case, which is if the inputs are vectors. So the easiest case, and sort of the one that we can actually visualize, because we can visualize it in only 3 dimensions, where functions from 3 dimensions into a fourth are obviously 4-dimensional. If we're sort of looking at a space function from 2 dimensions to 3 to a third, that's obviously can just be represented in 3-dimensional space. And I mean, the picture you want to have in your head is basically a surface. So the idea is that you have this plane, this flat plane that is your input space. And then some height above it, you have a surface where the height of that surface at each point is representative of the value of that function at the point. And conceptually, one could think about this in sort of 2 different ways. The sort of easiest way to think about it, probably for people who are sort of coming into this, would be to say it's actually not a function of a 2-dimensional vector, it's a function of 2 separate 1-dimensional inputs, right? So the idea is like you have an x value and a y value, and then you multiply them, you have like an x function and a y function, you combine them, and you produce some composite function. And that's a perfectly valid way of thinking about it. It's also valid to think about it as a vector. So you can see sort of the 2 ways defined here, one where I actually have 2 inputs and I plot it out. And down here, here's another example where I actually only have 1 input, this vector valued v as my input. And then I produce the same thing by acting on the xy vector. So these curly braces mean I'm passing it the vector xy, as opposed to up here where I pass it x, and then I also pass it y. And as hopefully you can see looking at the 2 of them, these are actually the exact same shape. Because you can look at a function the same way. This is the exact same function. I'm just thinking about the input space a little bit differently in the 2 cases. And there are advantages to doing it in either way that one should bear in mind. But seeing as I only have 1 person listening in, rather than go on to that, I should just ask, so like, are you familiar with this? Is this like comfortable for you? Are you comfortable with one or both of these forms? Any questions?
Technically, I think I'm all right. I think I'm okay. I can understand.
Yeah, and just feel free to shout out any questions, right? So, so there are really a bunch of reasons why you might want to do it one way or another. Like I say, it's probably a little bit conceptually easier to think about a function as just a function of 2 separate inputs. When we're doing the actual mathematics, when we're actually putting pencil to paper and doing calculations, it's usually easier to do it that way because, in that case, you're really working sort of component form with vectors. That's really treating a vector as 2 separate scalars. And then obviously some functions, sometimes it matters what function you're dealing with. So some functions are sort of best imagined as the result of 2 separate inputs, which then vary in an independent fashion. For example, you've probably, you've seen PV equals nRT, right? pressure times volume equals the quantity of gas times a constant times the temperature. So if you wanted to solve like what the volume is, and you had V equals nRT over P, then temperature and pressure would be separate variables there. You're not really in a vector space with temperature and pressure as separate values for the vector. In some cases, you might want to think about it as a vector space, and that would be what's called a phase space, meaning a vector space that's the arrangement of a system. But most of the time, you want to think about those as like separate things. However, there are reasons why you might want to do it the other way, because you might want to actually work with the input in the form of a vector. So what I mean by that is you might want to do a coordinate transform. You might want to solve the problem using a polar input versus a Cartesian input and switch back and forth between them depending on what's going on. And if you're doing that, you really can only do that if you have a notion of this thing as a vector that you can work with. Okay, it's spherical now, it's polar, now it's cylindrical, now it's back to Cartesian. All of that sort of only makes sense with vectors. Or you could ask like, if the dot product of my input with itself, if its magnitude is this, what could that tell me about the output? How does the output vary with the input magnitude? Things like that, which are really only a question that you can ask if you're thinking about it as a vector. And then, of course, some functions really are best understood as acting on a unified vector space. Coming out of 7D, the electric field permeates R3, so real space, and that's a vector space. And the electric field is coordinate system independent, right? If I change what my X, Y, and Z axis are, I should get the same electric field, just with a new form, because my X, Y, and Z are all different, but it should be the same thing. So we want some things to really be acting on 3 vectors. And then obviously, as you get more advanced and you sort of look at more advanced concepts like reciprocal spaces and 1 forms and 2 forms, which are beyond the scope of this, really you want these notions of vector spaces as your input. And just like last time, now that we have this notion of a function of these vector spaces, of a function of multiple inputs, we need to take our pre-existing concepts in calculus and upgrade them into our new environment. And the key concepts we want to upgrade are continuity, derivatives, and integration, because that's what calculus is, right? Calculus is essentially, and I've said this last time, I'll say it this time, I'll probably say it 3 or 4 more times at the very least. Calculus really is the study of how local and global behaviors interact. If I'm looking at something on a small scale, how do a bunch of small scale things become large scale? And how can I look at something on a large scale and determine small scale phenomena? And we have derivatives to move from large to small, and integration sort of to move from small to large. In continuity, just as an idea of really the local, the small, and the large really are the same behaviors. But first, even though before, normally in calculus, you need to know if a function is continuous before you can even talk about taking its derivative. So it sort of makes sense to start with a definition of continuity. It actually sort of here, probably better to start with our definition of derivatives. In part because the continuity for higher dimensional space is a little bit weirder than the continuity for just the reals. Then we'll address integration. There's sort of multiple ways to do integration. We'll be looking at one of those ways today. So if I'm going to stop sharing real quick, and I'm going to share my whiteboard. Way back when we were talking about having our multidimensional function here, and that one of the easiest ways to sort of analyze this thing would be to take a planar cut, to cut the function along some plane. That's a terrible plane, and turn it into a one-dimensional function again. And then, so this is exactly how we want to do our notion of derivation. Because obviously, if you have some point on a surface, there's no obvious forwards, right? You could choose any direction as sort of the minuscule step. And if we remember, a derivative works by taking sort of a minute step, and then drawing a tangent line through it. or really by taking the limit of tangent lines, sorry, as we move our 2 points closer and closer together, then, I could choose these lines however I'd like. I get totally different things. But if we take a cut along one axis and treat this as a function, let's say, this is the x-axis along here of like function of x, and then like a specific y naught, that's a constant, and turn that into f of x, we can take our derivative just fine again. We can say, okay, if this is just like f of x, then the derivative is well defined. And conceptually, that's what we want to do, and it's called a partial derivative. And it's called partial because it's only the derivative with respect to one axis. You can sort of think about this as like the derivative of part of the function, the derivative of the function as it is a function x. And mathematically, in terms of how we would define this rigorously, we do this by taking the limit as h goes to 0, just like a normal derivative of our multivariate function f of x y, and now we say f of x plus h comma y minus f of, that's a minus, let's just put a new minus sign in, x y over h, right? So basically what we do is we take the derivative of this with some constant y. We treat all our other variables as constants. And usually this will give us out a solution that like depends on the value of our constant. So like if we had f of xy equals like x squared plus y squared plus x times y, then the derivative of f of x y with respect to x is just 2x plus y, right? Because y is a constant, we know how to take the derivative of this very easily and get a solution. And this solution has a y dependence. In other words, this derivative produced a new function, let's say capital F of xy. Like it still has a dependence both on the direction we're in, and basically the x here is like where on this plane we are, and then the y is where we took that planar cut, determines the derivative. And we could have done this just as well as like y plus h, f of x, y plus h. And in this manner, we can access sort of the derivative along any axis. But there's actually ways to access the derivative if you are curious about like a shift along some arbitrary curve. We have a way of doing that. But first I want to go back to our nice little Mathematica thing and also see if there are any questions. Because I'm lecturing again.
No, that's fine. Yeah, I could. Yeah, I managed to understand that. So I got none.
Cool. And so one thing to note is that we don't use the same symbol for a partial derivative as we do for a regular derivative. We use, oh, I forgot to put my little split in. We use this guy, this weird curly D, and it's just pronounced partial. And there are two notations that are commonly in use. Just like with the regular derivative, there's a few different ways of writing it. Perhaps most conveniently is to write the partial derivative symbol with a subscript in the direction. The other way to do it is as a fraction, partial f of xy over partial x. And this is what we mean when we say a partial derivative is a derivative with respect to a variable. Note that df dx is also defined. There's another meaning for a total derivative with respect to a variable that's slightly different than the definition for a partial derivative with respect to a variable. And that difference shows up when we have like f of y is itself a function of x, or you have a situation where these variables are interrelated, is basically when we start seeing the difference between a partial derivative and a total derivative. And so here you can see basically the same example I gave, where if you take a derivative with respect to other things. It's also sometimes you will need to state explicitly what variable is held constant in a partial derivative. This can happen, if you're taking a derivative of like f of x, y, and z, and where z is a function of x and y, and equivalently y is a function of x and z. And what I mean by that is sometimes you'll be in a situation where like x, y, and z are all interdependent. And so you can choose to like hold one variable constant, but not like both variables constant in practice. Or you could say, even though it's non-physical, even though it doesn't make sense, we'll hold both variables constant when we're taking this partial derivative, just to see what happens for some reason. And this is a big deal in statistical mechanics. It won't be necessary in E and M. In E and M, all of your input variables are going to be nice and properly differentiated. Properly independent, rather. Whether they're properly differentiated, I suppose, will be decided by how good you are at doing the differentiation. And the other thing to talk about is restriction to an arbitrary path. So restriction to a curved path, for example. So let's say I wanted to go, and I'll go back to the whiteboard. I wanted, and I'll go to a new page. I have my, function here that's some like weird plane, like warped plane. And I want to restrict it to like some curve through it. And so now my cut is this curved plane. It's not a straight plane, right? Like how would I go about calculating the derivative of that? Well, locally, a curved plane is actually flat, right? And there's two ways of thinking about this. This is what it means to take a continuous path, right? The definition of, or differentiable rather, the definition of differentiability, the fact that like this curve is sort of something that is differentiable, that doesn't have points on it. The definition of that is if you zoom in enough, it looks more and more straight. It looks more and more like a line. It looks more and more like a plane. And so, we can make that assumption by zooming in enough. The other way to understand it, and I said this before once, is you can, if you're trying to cut a curved path, you can still do it with straight scissors. Because locally the path is straight, it's just that the direction curves. And what happens if we're taking a planar cut not on the X and Y axis? Well, actually it becomes very convenient. For reasons I don't really want to go in and give the details of. If I have my movement in like this direction, and that's like cos theta sine theta in some direction, I can actually write, and this is some unit vector in some arbitrary direction r hat. We can say, or v hat's probably a better choice here, because r hat does mean something in certain coordinate systems. Df, should be using the partial, but we'll say like df ds. So relative to movement along this line is just going to be cos theta partial f partial x plus sine theta. So this is like the idea of a directional derivative. In an arbitrary direction, you can actually just compose out of the derivatives along each axis. And this actually comes conveniently enough from the chain rule, if you would believe it or not.
I'll choose to believe it.
Because you can actually write this as like df dx dx ds plus df dy ds. And then dy ds is that sine component, and dx ds is that. And then these are the sort of components. And so that's you can do the chain rule. And that's important to note. If you have a multivariable function and you're taking its derivative and you're trying to use the chain rule you need to expand. So if you have like some arbitrary ds here, you need to write it as df dx y dx dx ds plus, you know, and so on. You can't just have one of these. One of these won't capture the entire change. It'll only because there's changes in the function due to movement in both directions, and you need to include that. So if you're doing the chain rule, your chain rule, you can sort of think about it like as a tree, like that splits apart and then potentially meets back up, or you know, you could even split further if x was itself a function of like multiple things, you know, that'll eventually all join up at the end. So that's sort of how partial derivatives work. That's the whiteboard. I meant to go back to the desktop. And so that's how you can restrict to sort of an arbitrary curve. And just like you can take, you know, a second derivative, right? A second derivative means how much does my derivative change over time, right? What's the rate of change of my rate of change? You can do that just fine using partial derivatives too. And the definition of like the second partial derivative with respect to x, you know, partial derivative of the partial derivative with respect to x is just the same as the definition in the in the regular case, right? So if I have some function, I take its derivative with respect to x, and I get that. I take the derivative of that with respect to x, I get exactly what you'd expect, and it's the same thing. It's how up curvy I am, or down curving I am. And if I do it with respect to y, same thing, you get exactly what you expect to get. But because partial derivatives, unlike regular, you know, one-dimensional functions where you only have x, you could take the derivative with respect to x and then take the derivative of that with respect to y. There's no rule that says you can't. Or in this case, yeah, so that's that. Or you could do it the other way. You could take it with respect to y and then take it with respect to x. And so what that represents conceptually is if my partial derivative, my second derivative with respect to x is sort of how does my x derivative change as I move in the x direction? All this is asking is like, as I move in the y direction, how does my function change? Like, how does the second derivative or the first derivative with respect to x change? So you can sort of think about that as how twisty the function is. Twisty is, you know, very, very general, but like if I start flat, like, you know, I'm a parabola like this, I start flat, but as I go outwards, my parabola starts bending down, you know, until it eventually like bends downwards over, you know, a long enough distance. That sort of twist downwards, that's captured by the idea of a mixed partial derivative. And if you're in a two-dimensional space, I did it again. If you're in a two-dimensional space, there are abstractly, you can think like 4 different second derivatives that exist, right? You can say, what's my partial derivative, or 4 different second derivatives that exist. You know, derivative with respect to x, so second derivative with respect to x, second derivative with respect to y, derivative of x with respect to y, and then the second derivative of y with respect to x, right? So you have these cross terms. Now, it happens that you actually only have 3, because as you can see here, it didn't matter what order I did my second degree partial derivatives, my mixed partials. This is a fundamental rule called the equality of mixed partials. If a function is C2, meaning it's continuous, its derivative is continuous, and its second derivative is continuous, I'm pretty sure C2 goes up to second derivative, then this is true. Doesn't matter the order you do them. You can do your partial derivative with respect to y and then with respect to x, or with respect to x and then with respect to y. Because of this, you often just write them in the same symbol. So you put xy down there to mean once with respect to x, once with respect to y. And you could even do like xxy to mean with respect to x twice and then y once. Because this rule works for higher degrees too. Like derivative of like xxy and xyx are also going to be the same. And I don't have time to actually prove this. Actually proving this is not easy. But there's sort of an intuitive proof we can do. And I've spelled it out here, but without a diagram, it's going to be pretty hard to follow. So, and I apologize, I'm hopping between screens a lot. We can sort of think about this proof by looking at the function across a little square. And we choose to make this square small enough that we can linearize our function. Then we have, an initial point, x, y. And then each of these lengths on this square are some differential distance x and some differential distance y. And if I wanted to ask so over here it's x plus dx, y plus dy. If I wanted to know how a function changed by here, what I could do is I could write f of x, y, right? Like that's the base value. Then I could ask, how does the function change as I move, let's say, to the right here along this little dx? And that would be, actually, I have to draw this because I can't put in the special symbols. That would be like partial f. I can draw partials. Partial x times this dx, right? Because my function is essentially linear. So I would have that term. And then I could ask, so that's the function here, right, is f plus that. And that's at here, then we move to there. And then I could ask, how does it change when I get to here? Well, that would be partial f partial y, right? Well, not quite. It would be at the new position, x plus dx y of this partial times dy. And like, what does that come out to be? What's this derivative? Well, if we think about the derivative function as we move along this square, then the derivative function here is going to be the standard derivative. It's going to be partial f partial y plus partial x partial f partial y times dx, right? Because we can assume the derivative is approximately linear. So we can do this. And so we can see here a mixed partial term of the form dx dy, as well as the regular one. And this is all going to be multiplied by dy, right? So we have the partial with respect to x times the partial x, the partial with respect to y times the change in y, and then we have this mixed partial term times both, dy dx, or sorry, like first derive with respect to y and then derive with respect to x. Now, as you may imagine, I could have also gone the other way. I could have moved upwards first and then to the right. And I'll save you me writing this out again. But what you will see is that this term's going to be the same, but then we get two new terms. We get this term again. We get this term, like this term again, just fine. But instead of getting this mixed term, we get another mixed term, which is in the other order. Because we go about it the other way, we have to swap the order here. So we get this term. So we have this term and that term are so the difference moving this way versus moving this way is the difference of these terms. But that difference has to be 0 because the function at that point just has some value, right? It's not like depending on which way you go, you get a different value of the function there. It's a function. It has only one value at any point, which means that the difference here must be 0, which means these must be equal. And that means this must be equal to that. And that's how you prove the identity of mixed partials. Now, in fact, the proof is a little bit more complicated because the second order term is essentially a quadratic term. So you would need to handle the dx term and the dy term, but I assure you, chugging through all the numbers, you'd get the same result. And so here's just the same proof as above. This is the same thing sort of written out fully, and you can go back and sort of like pause the recording, or do you have any questions about like that argument for the equality of mixed partials? Does that all make sort of some sense?
Oh yeah, sorry. I had to mute myself. My bad.
No, yeah, you're totally fine. You're totally fine. Mm-hmm. But yeah, and that's how we know the equality of mixed partials. But yeah, now on to continuity. And I have this here as continuity sequence break because it turns out you got to do this in a slightly different order, and also because it's a pun about continuity. So continuity is the following. So continuity on like a two-dimensional space, like the formal definition that you would learn if you took topology, if you took a math class, basically, is a little bit complicated. It uses phrases like open sets and pre-images, but to simplify the explanation, we can just say a function in multiple dimensions is continuous if its restriction to any continuous path is itself continuous. So the idea is a function's continuous if no matter how you like trace your way through the function, you're continuous. Whatever arc you choose to take through your function, like when you restrict it to one dimension by taking, those parametric lines through it, like we saw those planar cuts, then we get continuous functions whenever we do one of those restrictions. And sort of a further simplification, and again, this further simplification comes from the claim that you can cut curves using straight scissors, is the function is continuous if it is continuous along any line through a point. So if you take any straight planar cut through a point, the function's continuous through that planar cut, no matter your choice of point or line. You can say it's only continuous at certain points if it's only continuous for it's continuous for all cuts through some points, but not through other points. Then it's continuous at those points where you can take those cuts. So the obvious definition would have been a function is continuous if it's continuous in both x and y. But here's the counterexample. Does this function look continuous?
No.
No, it doesn't. But if we actually take its cut through the origin along x and y, it produces two perfectly continuous functions. Like this is just the absolute value function. This is just the 0 function. Those are continuous. Like if we line it up here, like there's a continuous line through there. That's just the absolute value you can see here. Along here, it's harder to see, but that's like just the line, a flat line. But if we actually look at it in higher dimensions, it's not continuous. So how can we check this conveniently? Well, we can, if we think about any line that passes through a point, any line, there's sort of two kinds of line. And I'm going to say something very obvious sounding. There's vertical lines and lines that aren't vertical. Feel like all lines can be pretty easily categorized into one of those piles or another. Lee, I see you just put the question in 2 minutes ago. I'm not. This is for physics 7D. I'm just helping out explain multivariable calculus as would be necessary for physics. But I mean, you can hang out too. I don't mind having more people hanging out. If you have any questions, whatever, this is, and if you have a question and it is Max around, like if you have a question, I can also potentially handle it during this time slot. But sort of, it's sufficient then to check all the vertical lines. There's only one of those, right? Hold X constant and vary Y. In other words, set X to some value, which is the value at some point, and treat Y as a variable. Is your result continuous? Yes or no? And then the other thing you need to check is all functions, all lines that can be written like xy is equal to t and mt, right? And this is just all lines that pass like that are like look like this: y equals mx, right? For any m, we have to consider all possible values of m. And you might recognize y equals mx. That's just a linear function, right? That's a linear function with zero intercept. That intersects the origin. So the reason we had to break out the y case from this case is, you remember the definition of functions, they have to pass the vertical line test. The vertical line itself, perhaps ironically, does not pass the vertical line test. So that's why we need to consider the y variation separate from all other possible variations. And then we can just put all the other variations in by writing y equals mx and using that with x to determine continuity. In the case of the above thing, if you wanted to know where does this fail, like why isn't this continuous, all you would need to do is set m equal 1. So the line just like x equals y, because then the sine function has no idea what's going on. So you have no idea, like, am I supposed to be positive? Am I supposed to be negative? Am I supposed to be 0? What's going on? And that's like where continuity breaks down for this function. And also I see we have Navia showed up. I'm glad to have you. The more the merrier. But that's sort of how continuity works. And if anyone has any questions about continuity for higher dimensional spaces, I need to pause to drink a little bit of something to just dry my throat or wet my throat. So. And like, I really do appreciate you guys showing up. I know I already said that earlier, but it's nice to feel like people care about the subject. And about math, because math's fun on its own, even without physics. But if there are no questions on the continuity front, we can move on then to area integration. So when you're integrating a higher dimensional function, there's actually a few different ways you can do it. There's either area or volume integration, which can be thought of as integration over a subset of the domain with 2 or more dimensions, or line integration, which is integration over an oriented parameterized curve within the domain. And we talked about orientation for curves before last time, but sort of talking about area or volume integration, which is what we're going to focus on today. That's just integration over some subset of your space. Typically, it's an integration over a subset with the same dimensionality as your original space. So if you have like a function through 3-dimensional space, usually you're taking volume integrals for that. Sometimes you'll be taking surface integrals for that, which is, an area integral, but usually you'll be taking integrals using the same number of dimensions as your original thing. And like I say, we're going to be starting with area or volume integration, not particularly because it's easier or will be useful in the other case, but because Gauss's law is important. For tomorrow, in fact, you're going to be doing a problem set on Gauss's law if you're in Physics 7D. So probably good to get comfortable with it. And so here's sort of the easiest example of what does it mean to do an area integral. This orange thing here is this function up here, 9 minus x squared minus y squared. And then the question is, how do I find what the total volume inside, like between this 0 plane and the function is? Sort of what's the volume, say, contained within this cut, this little shape here, along the 0 plane on the bottom, and then my parabola up on top. And that might be a pretty hard question for you to answer off the top of your head. Like, how can we calculate arbitrary volumes? And technically, I want to know this is an area integral because you're integrating over the area of this blue square. Even though you're finding a volume, you're finding volumes through area integrals. I did not come up with these terms, like at all. Well, the obvious thing to do is to make an analogy back to how we found areas using integration in one-dimensional calculus, right? So do you know what a Riemann integral is? A Riemann sum?
Yeah, I'm familiar with that.
Yeah. So depending on the depth you went into it, you understand it as either taking a bunch of small segments of an area of a length, or you might know it as the infima of the suprema of the product of the lengths of each element of a partition times the suprema of that partition versus the suprema of the infima of the same if they are equal. Probably haven't heard that version. So there's a few, but basically the idea is we know what the length, the area of a rectangle is, and we know how to cut a function into a bunch of small intervals where basically it's the sum of rectangles. And what may be completely unsurprising is that you do the same thing here, except instead of using a rectangle, you use a rectangular prism, right? So if we take a bunch of rectangular prisms and do the cut, we can see that as we make the rectangular prisms, which are really square prisms, smaller and smaller, right? We eventually get something that looks an awful lot like the original function. And man, Mathematica does not like rendering it at that small size. Let's go with something a little bit better. And you can even see that these still are little rectangular prisms, but it ends up looking like this. Now, obviously, the proportion's a bit different. Unfortunately, there's no real way to tell Mathematica efficiently what proportion to draw this. But, we have this idea. And, that immediately sort of probably suggests to you how to do this. But in case it wasn't obvious, how do we take the sum over each of these little squares, each of these little rectangular prisms? The answer is, well, we can do it for like a cut. So we can go up here and we can take like the first row. And, we can calculate it, like we can take the sum over each element in the row. And then what I'm doing here is I slowly move across each row. Yes, multiple integrals. if we just integrate like in one dimension across each row, we get this area. And this area, we can then integrate each of these together. Exactly. So, you know, if this is our definition, right, of the area of a rectangular prism, it's height times length times width. So the length and width are both, you know, our dx and dy are differential unit lengths. And then the height is our function. We approximate our total volume as the sum of our function times dx dy across all the small squares in our little square, in our big square. And then we decompose that sum into the sum of sums, right? We sum over x, and then we step out and we notice that this here is a constant, is a function of y. And then we step out and we sum across all possible values of y. So we take the inner sum across x, outer sum across all y. So what this means is when we upgrade, and you probably remember, when you upgrade from sort of the discrete case to the continuous case, all you do is you replace a sum with an integration sign, and these dx and dy become the sort of terminal symbol on the integration, a little dx at the end of an integral. We just integrate across x with y arbitrary and fixed. In other words, we treat y as just some unknown constant and take the integral, and then we integrate across y. So when we do the first integral across x, all the dependence on x will go away, right? Because you're integrating across x. If you integrate like f of x from, you know, x equals 1 to x equals 5, that's no longer a function of x. So that goes away. And then when we integrate across y, all the dependence on y goes away. And so we just get a number, and that number is exactly the area integral. And you can actually do this with respect to x and then with respect to y, or with respect to y and then with respect to x. So this is it here. If we have like f dA, that's just f dx, and then take a step out, f dy, or rather this thing, dy. We can do that in any order. And in fact, if we're dealing with a 3D function, we do it dx, dy, dz, or for that matter, any of the other 5 ways of doing it. Right? There's 6 total arrangements of the order of integration. Sometimes it makes sense, like what order you do them in doesn't matter. There's a footnote on that, which is it sometimes matters, but only if you're dealing with really, really awful functions. Like if it matters what order you do them, something's gone horribly wrong, and what you're looking at isn't anything you should ever be working with without like a lot more math. Because at that point, you can't take an integral. At that point, your integral is ill-defined, at least in this manner. But you can do them in any order. And sometimes there's an art to selecting the order, because sometimes you can do it so that like the inner integral is 0, and then you're done. Because it doesn't matter, you're just integrating 0 by something, right? If you choose like the order you do your integration, you can get cute about things. So let's do that above case. So we integrate this parabolic function with respect to x from x equals -2 to 2. And we get exactly what we expect, right? That's just the integral of the initial function with respect to x from -2 to 2. And then that can be integrated with respect to y to get that. And you can see if we do it in the other order, we get the same answer. And that, in fact, is the volume of this, which is also equivalent to the volume of this thing as I make my squares arbitrarily small for rectangular prisms. And that's also the sum of the volumes of each of these cuts. That's all the same idea of what it means to take a volume integral. Does that all cohere? Does that all make sense?
Yeah, it makes sense to me.
Awesome. So now we've got an idea that's pretty good for if I want to integrate across arbitrary squares. Or like, for that matter, arbitrary cubes if I'm doing a volume integral. But sometimes I don't want to integrate over a square. Sometimes I want to integrate over like a triangular shape, right? Like what if I wanted to integrate across like one of these triangles? What's the area, or rather the volume between this and like here? Like what's that volume? Well, you might think, oh, well, I could just change my axes, but there's sort of an easier way of doing this that's also sort of far more universal, which is when we were setting up the integral here, you notice the bounds of the inner integral were like minus 2, 2, right? That's like the length in the x direction of our integral. But in fact, and hi and welcome, glad to have more folks showing up. Are there any more theorems? In what sense? There are many more theorems. But I'm getting to the end here on Gauss's law, which is sort of the big, one of the big three, I would say, results from vector calculus for the purposes of physics. And everything I'm presenting here is often like the truncated form of like, there's like a proper name for the theorem that says you can interchange what order you do your integrals. That's not like, it may seem obvious that that's the same thing, but as you know in mathematics, it seems obvious isn't a good proof. So mathematicians actually have to do work to get this. However, we're physicists. We get to steal results from mathematicians. It's one of the best parts about being a physicist. And again, funnily enough, of course, I say that as a mathematical physicist, which means I'm the type of physicist that doesn't get to do that does need to justify his claims. Which is why I can assure you that this works. Pretty much. But to go on to explain to how to do this case. Remember, the inner integral here was only a function of like, it wasn't even a function. It was just from like minus 2 to 2. And that's probably how you're used to seeing integrals. But in fact, the function on an inner integral, the bounds can be a function of an outer integral. And so it's a little bit hard to demonstrate that in Mathematica because Mathematica is, and this is a highly technical description, ugly as sin. It's even worse than my handwriting, really. It's amazing that like I can do anything in it that's educational. So the idea is basically, let's say I have my multiple integral, right? What I can do, come on. And I promise my handwriting will improve when the iPad arrives. Not by much, because my handwriting's also just terrible, but it will improve. So let's say I was doing it like in terms of x and then y. I could integrate like from minus y to y on my inner integral. Now I couldn't do it out here, because then like by this point, like I'm integrating with respect to y. I couldn't even do it with respect to x out here, because like x is no longer defined. Like what's x, right? Because this got rid of all the x dependence. But in this inner integral, we have like some unknown y position, right? We haven't resolved this y, so y is some unknown constant. And just like, you can always take an integral from like a to b, right? You've probably done integrals where like a and b are just unknowns, and like you're integrating x from a to b is, equal to b squared minus a squared over 2. Same idea, I could put like y up here. There's no reason I couldn't like use y and minus y and get like y squared minus y squared. So in this case, it would be 0. But you get the idea. I can integrate like any function up here. And it doesn't need to be simple. Sometimes you might want to take like the integral of like the square, from like 1 minus x squared, and like minus root 1 minus x squared, my function dy, and then integrate from like x equals minus 1 to 1. And bonus points, and I can't hand out cookies for multiple reasons, but bonus points and a cookie to anyone who can tell me what this shape represents. What area is being integrated over by this double integral? Oh, and how do we solve? Not quite. It's not quite a parabola. So y, So when is this at the maximum, and what is it? Like at the maximum, it's on the y-axis. It's like y is -1 to y is 1. And then like at the maximum x distance, like 1 and -1, like it's 0 here. Then like what is it? It's some sort of shape that connects these dots. And so like look at this as a function of x, and this is a function of x, and you get two like lines here. And what shape does that make? Also, I see the question like, how do we solve the integrals? At the end of the day, you solve the integrals how you would solve a normal integral. So for all of the complexity up here, this just looks like a normal. This really is just a normal integral. It's like some function with respect to x, dx, and then you just plug in your bounds, right? You solve your integral normally and then substitute these in to the resultant indefinite integral. So you take the indefinite integral, sub in y, and then subtract the indefinite integral, sub in -y. But yes, going once, going twice on what shape this winds up being. Circle, yes, it is the unit circle. And that's not a circle, but this is. This is exactly the unit circle. So if you were trying to integrate something across a unit circle, you'd use these bounds. I mean, more realistically, you'd probably want to do it in polar coordinates, but if you wanted to do it in Cartesian coordinates, you would use these bounds. And that'll come up a bunch. And you can even, if you wanted to go one step further, you could subtract here minus z squared. Replace this with root 1 minus z squared. And down here, negative root of 1 minus z squared if you were like dealing with a 3D function. And then from -1 to 1 dy dx dz, God, sorry. And then this would be a sphere. And the proof, the proof of that basically comes from actually tracing out the bounds. But yes, you would both get cookies were I blessed with that power. Unfortunately, I am not. So we hop back over. And yeah, this is what I was just saying. You could even do it over like a larger boundary. And as you can see, I'm doing that case here. So I'm integrating from z is the square root of r squared for some r squared minus x squared minus y squared. And I do it again with, over y squared varies from minus r minus x squared to plus r minus, do it that way. And you can see actually when I do that integral, and I'm using the identity. So I'm using a thing basically that doesn't change the volume at all. That's sort of a four-dimensional space with fourth dimensional height 1. You see that doing this integral actually gets me 4 pi r cubed over 3, which is the volume of a sphere, which makes a lot of sense. If I'm integrating, the identity over the contents of a sphere, I should just get the volume of the sphere back out. Just like, if I integrate the identity over some area, one could see how you should get that area. Integrating the identity over a volume should get you that volume. So here's an example that if people want to take a shot trying to do, consider this integral and using the methods developed above, find the volume contained between the function and the 0 plane within this square. So find what the total volume there is. And I'm going to mute myself briefly to give you guys a chance to work on that. I'll be back. Not be back. I'll unmute and I can handle any questions if people have issues. But I'll continue explaining things in a couple minutes. Uh, I know it hasn't been very long, but does everyone have an idea of where to start? Has everyone sort of gotten started? Yeah, it can be hard to sort of apply these unfamiliar concepts initially. I promise at some point this is going to be just as easy as taking a regular integral, which, I mean, integrals aren't exactly easy, but, you know, it's not going to be any harder. Yes, you will need to take a double integral here. Oh, and I realize you can't see my split timer at the moment because I was only sharing the Mathematica notebook, not the full screen. How bad of me. Not that it's particularly relevant to anything, but you know, I think it's funny. There are jokes there. Maybe not good jokes, but there are. You treat it as a constant. You treat it just like you would sort of treat, like if you were integrating, like as a very basic example, like ax squared, right? What's the integral of like ax squared? It's ax cubed over 3. Same thing. It's just sort of a chunk of nothing. So like, what's the integral like of a constant with like over x? Like, what's the integral of some height? You know, it's just x times that height. Yeah. And that's basically the big secret of this, is that you leave your variable sort of unknown and you just treat it like some constant. You know, I went with arbitrary boundary execution as like a joke on arbitrary code execution, but I realized there's an obvious like out of bounds glitch joke to be made there. I'm the worst at coming up with these puns. Thanks. Thanks, seriously. Oh no, these are references to speed running. Because in an early discussion group, someone said we were speed running multivariable calculus, so I went with it. I suppose arbitrary code execution is a bit of a deep dive for speed running, but if you ever see those like task runs where they basically overwhelm the buffer and just start inputting arbitrary code into the thing, it's beautiful. Yeah, this is probably a good time to, if you didn't quite get a final solution, that's fine, but it's probably good to move on because there is a bit more to cover, unfortunately. So the first step is to integrate with, you could have done it with respect to x or with respect to y, but do the integral with respect to one of the values, treating the other as a constant. So coming up here, we see 1 plus y squared is a constant, and we expect that to be multiplied by x. And so it is, and let me just do this as an indefinite integral. Right, so that's the indefinite integral you get. So you integrate like the 1 plus y squared is a constant, so you get a factor of x on that, so you get x plus xy squared, and then you get the integral of x squared is x cubed over 3. And then you plug in your values for that of -1 and 1, and you get this. And you get this function, and you do the same thing. What's the indefinite integral of this? Well, it's going to be 2/3 y plus 2 y. So that's going to be 8y over 3. Plus, what's the integral of 2y squared? Well, that's just going to be 2y cubed over 3. And then we plug in -1 and 1, and we get 20 over 3. So indeed, the total volume contained between this, I don't know exactly what to call it, sort of warped plate, and the plane is 20 over 3. And now we move to the section I labeled double the difficulty, double the fun. Spoilers, it only doubles the fun if you think this is fun. So for me, I'm having a great time. I don't know about you, but I'm having a great time, which is, what about multivariable vector functions? And we take ideas from the last lecture. I call it a lecture. I mean, it's just me talking at a screen, but I mean, you know, that's what a lecture is, I suppose. And so we can have a vector function of two variables. So here I have, you know, what's the vector xy, and I'm saying it's yx. So it's like the vector of flipping the x and the y. What does that look like? Well, it looks like this vector plot. As you can see, like when y is positive and x is 0, it just points in the plus x direction. When y is negative and x is 0, it points in the minus x direction. Along the plus x, it points in the plus y, and the minus x, it points in the minus y. So you can see that like this is what this plot ends up looking like. You can even do a three-dimensional vector plot. You can even do a 3D vector function. They look like this. Mathematica doesn't do a very good job of showing what these look like because nothing can do a very good job of showing what these look like. Picturing these can often be pretty hard, but we can just, we remember the tools we developed from last time, which is we can think about this as a separate z, you know, x component function, a separate y component function, a separate z component function, right? So we have like fx here equals y, fy equals x, and then like fz equals z times x plus y. And then our overall function is just, you know, the x, fy, fz. And now each of these is itself now a function of x, y, and z. And so you just have a bunch of multivariable functions in a vector, and you can get a vector function. Nice, and it's simple eventually, promise you. And now we're on to divergence and Gauss's law, labeled here as no time to explain, because this is a big thing. This is a big, fundamental, huge pile of ideas that we need to get through. Divergence is a property of multivariable vector fields. It's not a property that exists for a vector valued function of one value. You know, it's not like a property that a parametric curve has, and it's not a property that a surface thing like this has. It only exists for these guys. And it only exists for these guys because it's basically an idea of how exploding a function is. And it's sort of like a combination of the sort of same direction derivatives. And like, what do I mean by that? I basically mean like, if I move in the plus x direction, how much does my x derivative increase? If I move in the y direction, how much does my, not y derivative, sorry, how much does my x vector component increase? If I move in the y direction, how much does my y vector component increase? Basically, if I move in a direction, how much does my vector increase in that direction? And so it's defined like this. So we write the gradient as this upside down triangle dotted, this should be a central dot. This should be like a dot product dot, but I can't make that work too well in Mathematica because I'm bad. So I'm just using a dot here, but this should be in the middle. And this upside down triangle is called nabla, or sometimes grad. But nabla dot f of x, y, and z, and that's, so we remember that like fx is the x component, fy is the y component, fz is the z component of our vector up here. We define it as partial x, fx, partial y, fy, partial z, fz, and we just add them together. So this was a vector valued function, but this is the derivative of a scalar. The partial derivative of a scalar is a scalar. The partial derivative of a scalar is a scalar. The partial derivative of a scalar is a scalar. It's the sum of scalars. So this is a scalar. This is just a number. I mean, it might be a function. It might depend on x, y, and z, but it's just going to be a number that depends on x, y, and z. And what it does is it's looking at the partial derivative of each vector component along the axis of that component. And just like one might hope, if we wanted to do this in only 2 dimensions, we could just remove the z components and we'd be fine. And in fact, if we really wanted to get fancy, we could even add more dimensions in the same way. But don't do that. There's no reason you should do that. But yes, so this is a scalar quantity because it's the sum of scalars. And what it represents is how explodey the function is. So we have an example here. Here's a function that's sort of exploding outwards from a point. So it's going to be positive because we can think about it as like it radiates away from this point. It's leaving this point in the center. In fact, it's hard to tell, but this function actually is leaving every point. Mathematica does a terrible job showing the relative magnitude of vectors because it seems to think we want them color-coded instead of using lengths. And I don't know why it does that, and I'm sorry. I've tried to fix it, can't. But so we can calculate the divergence here. There's a Mathematica command, we get 2. Another way of seeing this is our function is xy. So the partial derivative of the x component is x, the partial derivative of x with respect to x is 1, and the partial derivative of the y component, which is y with respect to y, dy dy is 1. So we have 1 plus 1 equals 2. And that's how we get this divergence here. And that's 2. And so that's a positive value because it like explodes out. We could do it the other way. We could do minus x and minus y. And then as you can see visually, it sort of looks like it's collapsing inwards, like imploding. It's going into a point. Instead of exploding outwards, sort of like flowing in. And so we get a negative divergence, right? Because the derivative of minus x with respect to x is -1. The derivative of minus y with respect to y is -1. So we get -2. And here's another case like where we're doing x squared and y squared. The derivative of x squared with respect to x is 2x. And the derivative of y squared with respect to y is 2y. And so now the divergence is 2x plus 2y. It's actually now dependent on position. It's not just a constant. It doesn't always need to be. This is the plot of the divergence. So you can see that it is actually a scalar valued function. There's one other case I want to look at briefly, which is if I do a vector plot of the function y comma x. So here we have the derivative of of y with respect to x is 0, and the derivative of x with respect to y is also 0. So this produces something with a 0 divergence. And indeed, if we take div of yx comma xy, we get 0. And so this doesn't really explode from anywhere. It sort of swirls, sort of even more obviously circular if we put the minus in on like x. So it's like swirling around a point, but it's never like leaving or entering a point. It's just moving in a pattern that doesn't really explode out or collapse into any points. So now we get to Gauss's law. Gauss's law states that the volume integral of the divergence through a volume is equal to the flux over the necessarily closed boundary of that volume. So if we take a bounding surface, bounding surfaces have to be closed, then the flux through that bounding surface is equal to the volume integral of the divergence. So what is flux? Flux is the area integral of the dot product of a vector function with the normal vector, which can also be called the differential oriented area element, because obviously that's way easier to say than normal vector of a surface. So mathematically, we write the flux like that. The flux is the area integral of some function with the normal vector, where the normal vector is like defined like that, of a surface, where A and B here are vectors along the surface. So if you think about like a plane, right? A 2D plane, there's sort of like vectors in the plane. And there's two vectors in the plane because it's two-dimensional, right? It's spanned by two different vectors. And there's one vector out of the plane, you know, perpendicular, that you can construct at any given point. And that perpendicular vector is the normal vector. And you can find that normal vector actually by taking the cross product of any two vectors on the surface. This is because if you remember, the definition of a cross product is it gives you the vector perpendicular to the vectors you put into the cross product. So if you put in two vectors on the surface, you'll get a vector perpendicular to the two vectors on the surface. So you'll get out a vector that's, you know, perpendicular to that surface. If you really, really want to be fancy, you don't normalize n. You instead use n to sort of geometricize the system in the same way, remember, we use the velocity, that like t derivative to geometricize our parametric curves. You can use the same trick with using the length of n to represent like the area covered by two vectors. But that's really fancier than we get to be. So this is super complicated relative to everything we've done so far. So we'll be looking at some examples. The examples we'll be looking at are all three-dimensional. Gauss's law actually still works in 2 dimensions because the cross product is the general case, or is the specific case of something that can actually be defined in 2 dimensions as well. If you think about what a cross product is, remember, like I say, it's that thing that gives you a perpendicular vector. In 2 dimensions, there's a perpendicular vector to any vector, right? You have like the vector 90 degrees from a vector. So you can take sort of a cross product of a single vector. Instead of needing 2 vectors to define a unique perpendicular, you can do 1, and that's just the normal vector pointing perpendicular to your velocity vector of a line, of a curve. So let's take an example, a very simple function, you know, x, y, z as our function for divergence. If we integrate the divergence, well, first of all, do we know what the divergence of this is going to be? It's going to be dx dx, dy dy, dz dz is just 3. And if we integrate that over the volume x from -1 to 1, y from -1 to 1, and z from -1 to 1, we get 24. And that may not be obvious. You can sort of see that really quickly. This is 3 integrated over a length of 2. So that's just going to be 3 times 2 over another length of 2 times 2 over another length of 2. So that's 3 times 2 times 2 times 2 is 3 times 8 is 24. So this is a box, right? -1, 1, you know, x varies from -1 to 1, y varies from -1 to 1, z varies from -1 to 1. That's a cube, right? If we go like graphics 3D, I can do this real quick. That's just the cube Ooh, I cannot do this real quick. One moment. What's the command for this? I should have written this in cuboid. Pretend that worked the first time. I was good at this. So that's like this cube. And like it's the divergence here. So the question then is, what's the flux of this thing through the cube? Well, what's the normal vector on each cube face? That's just going to be like on the, pretend like the gold side here is the plus z. So here it would just be like the plus, like it would be 0, 0, 1 pointing upwards. And that would be the plus z. And if this side's like the x side, then that would be like 1, 0, 0. And over here it would be 0, 1, 0 in the y direction. And then there's like the bottom face down here. And that would be, what's the normal vector here pointing outwards? That's 0, 0, minus 1. So let's do this. Let's integrate our function for our divergence over, we're going to start on the minus z face. So there, z is always -1 down here, right? This is the z equals -1 face. So we set that. We set the dot product with the normal. The normal here is -1. We integrate from x from -1 to 1, y from -1 to 1. We get 4, right? Because the function for divergence here is 0, 0, minus 1, because it's just x, y, z. Or, and it's not going to be 0, actually. Sorry. Correction. It'll be x, y, minus 1. But the x and y terms go away because the normal vector doesn't contain an x and y component. So instead of having to do like a really complicated integral, because we're taking this dot product, we cancel out those x and y components. We just have that z component times -1. We get 4. We do the upper surface. Now the upper surface, the normal vector, like I say, is 1. And we do that replacement with z equals 1. We do that same thing. We get 4. And we do that for all 6 surfaces. And we get 4 on each surface. So 4 times 6. What's that going to be, guys? That's going to be 24. That's going to be the same answer as when we got from the divergence, which it should be because that's what Green's theorem says, or Gauss's law, sorry. That's what Gauss's law says. So if we got a different answer, we'd have a problem. Let's look at a more complicated example. Let's say we start with the same function, but with the same divergence of 3. But now we want to integrate over a sphere. Well, we can integrate the divergence over a sphere using the same formula we saw earlier and get 4 pi. So this is like a volume integral over the internal volume of a sphere, and we get 4 pi. Now, integrating over the surface of a sphere is super complicated. But let's try it by integrating, let's say, first the top half. Then z is going to be that along the top half. And then these are the values of x and y. So we integrate with respect to y from this interval and x from this interval to make a circle. And then the value of z creates a dome on top. And we do the same with the dome on the bottom, like a bottom-facing dome. And so the sum of those two domes, that's going to be a sphere. So we get pi and pi. But that's not 4 pi. Now, you might want to think, oh, Charles made a typo in his code. That would be a very good guess. Statistically speaking, that's what happens. In fact, when I was writing this example, I initially assumed I did that. Why didn't this work? Well, up here, I was taking this integral over this surface of this normal vector, but I was doing it over these little squares, right, of y from some small range and x from some small range, and then letting z be a function of that. But the area, and I'm going to have to do this on the whiteboard, basically what I was doing here is I had a dome, right, my little spherical dome. This is the worst spherical dome in the history of spherical domes, maybe ever. A little spherical dome. I was looking at little cross sections, right? And then I so if this is x and y here, what I was doing is I would take a little section here of my little dome and integrate across it, this little square on the dome. But of course, the height of the dome, that's not quite a square. It's going to have a little lip to it, Remember when I mentioned a little differential area element? That little lip only is roughly a square if you're up here at the top of the dome. On the side of the dome, your little thing looks a lot more like that. And like the area of this little cut here is going to be way different than the top of the dome. So I would have to factor in the fact that as my X and Y were changing, my differential area element was changing in size. That's really hard. Like actually super hard. I was trying to do it for a little bit and I was screwing up. I couldn't get it to work. But that's why we use Gauss's law. Instead of dealing with the fact that like the differential area changes, and this is why writing like dx, dy, it can be misleading. You need to make some area adjustments, super complicated, where you need to replace this implicit unit element with something weird. If you were trying to find the flux through the sphere, you just want to use Gauss's law. The Gauss's law calculation was just, well, the divergence is 3, and the area of a unit sphere is 4 pi squared, 4 pi over 3. So 3 times 4 pi over 3 is 4 pi. Trivial, right? Super easy calculation. And in fact, from the above, this would be one of the ways you could actually calculate the surface area of a sphere, because you could work out that the product across that sphere would always be 1. The dot product will always be 1. And so the dot product 1 times the area of the surface of that sphere needs to be 4 pi over 3. We can use that to get the surface area of the unit sphere. There actually shouldn't be a factor of, actually, no, there should be. The flux density here is 3 everywhere. That was my mistake. So you can use that to calculate the surface area, actually, of a sphere. So that's Gauss's law. In some cases, it's way easier to use divergence to calculate flux. And in some cases, as you'll see tomorrow, it's easier to go, no, actually tomorrow it's divergent to calculate flux as well. Often that's the easier direction. Volume integral of a divergence gives you the flux. Sometimes it's the other way. Use the flux to get the volume integral of the divergence. And we're done. And we move to any questions you may have. And if we really have time, we've only got 15 minutes, I could try and show you why Gauss's law is true just visually, so that you don't just have to believe me when I say a bunch of math words at you with the implicit threat of offering a proof if you don't believe me. That's sort of if you ever heard the term argumentum ad baculum as the logical fallacy for making a threat to prove your point, that's basically what I'm doing here. I'm saying, if you don't believe me, I can bring out the math. Do you really want me to bring out the math? But I can bring out the math if you don't believe me, or if you have any other questions, I'm happy to take them now. And I apologize once again for how rushed that was. Cool. This is a super neat visual proof, actually. And I'm gonna do it in 2 dimensions. Because doing it in 2 dimensions is enough to get the idea. Doing it in 3 dimensions, it's the same, except it's way harder to draw. And a little bit longer. But what we're going to do is we're going to try and do Gauss's law on a very small square, right? Because the idea of physics, or sorry, the idea of calculus, as I've said before, as I'll say again, look at how things work on small scales and how they work on large scales. How do small behaviors come together to form larger behaviors? So let's look at some small square of differential length dy and dx. And let's look at that. So if I'm thinking about the flux through this square, right, and I define my little outwards pointing vectors along this square, right? The flux through this square, there's going to be two components. There's going to be vectors coming through this way, and whatever direction they point, we're going to only be looking at their x component here because of the dot product with the x component. So if anything here, we just project it along to that x component. There's going to be, over here, it's the same vector. We project onto the y component. In here, same idea, except we're projecting onto x with like a minus sign, right? So we have this tiny little square. And if I want to ask you, well, what's this component over here minus this component over here? What's the change here? So if my flux is like this way, what I can basically say, we can call this surface like the plus x, and this surface here like the minus x surface. Then my total flux through this closed thing is my flux at plus x, or rather is my flux at plus x plus my flux at minus x, and then my flux at plus y plus my flux at minus y. Now, what's that going to be? Well, it's going to be, remember, we're casting this, and let's say my function that I'm looking at here is fx, fy, is this is my vector function. And I'm, have it through all of this, and I'm doing this like projection trick. Well, over here, the flux here is going to be fx times x component, and then like fy doesn't matter. So that's going to be fx at the plus x plane, like along this surface here. And you might say, what about like the y height? Well, it doesn't matter, because the difference here and here, like what's the height difference here? It's some very small dy. We're just going to assume it's roughly constant across that. And then what's it going to be over here? Well, it's going to be the same thing. It's going to be plus fx at minus x y, but now it's times the minus x vector. So there's going to be an overall minus sign on this component. And the same thing is going to happen. So this is one component, and then the vertical component is going to be the same thing. It's going to be fy along plus, along this x position, whatever our x is, a little plus y. That's going to be minus fy at some x minus y, right? And are you convinced that this is indeed the flux through this little square? Yeah, I mean, it's sort of just like the definition of like the total flux. But then what is this difference? Well, this is a really tiny square. And when I say really tiny, I mean differential. So this difference here can be written as fx at x plus dx minus f, and then, sorry, y, x, y. And what does that kind of look like? Just visually, if I imagine what that is, kind of looks like a little derivative, right? That little buddy's a little derivative. It's not quite, right? I don't have my division by dx. Like that term's not there. There's a little derivative there. And it's the derivative specifically of the x component in the x direction. And then down here, this is going to be kind of sans, like I say, that's sort of missing the denominator. And so what does it mean to be missing the denominator? What if I was multiplying by the denominator? What if the denominator was there, but I was just multiplying by that denominator, right? Because that's the other way of writing this, is df dy times dy. So we have partial f partial x dx plus partial y partial f of x, partial fy. Sorry, got to move this out of the way. Partial fy over y times dy. But the flux isn't just this length, this bit, right? It's also multiplied by the length of this, right? That's like the flux from like this point to this point. What about like the flux from this point to this point and this point to this point, right? There's going to be another term there of that length. And what's that length? That's dy, right? So there should be a factor of dy over here. And up here, there should be a factor of dx associated with that length, right? Because it's not just like the flux through a point, it's flux through a point times that total length along that line. So up here, we have dx dy, and over here we have dy dx. And what's that? That's partial fx partial x dA plus partial fy partial y dA, right? And then we can just group these, right? You can just, if the integral of a sum is the sum of an integral, you can just write this as putting them inside. And here we're actually using that idea of the equality of mixed partials. We're using the idea that it didn't really matter what order we did our integral across. And what do we have here? We're done. That is grad f. And boom, Gauss's law, clear as day. It just works. Now, you might say, well, that only worked if you did it across a small little square. How can we be convinced that that works for like a big shape? Like maybe my shape isn't even a square. Well, what is a big shape? Calculus teaches us that a big shape is just a bunch of small squares. And you might say, well, maybe the sum works differently. Well, what happens when we have a bunch of squares together? The total flux here, right, is like the flux across here minus the flux here, right, like all of that. But actually, that's the same thing as adding this flux, like, and I'm going to have to draw this again. That's like if we have, let's say we have only two of these squares next to each other. The flux through here is like this flux on square one over here, right, is positive. But it's the same thing negative here, right? It's the same thing, but with a minus sign. So if we add up the flux through each of these small squares that are touching, all of the fluxes on the inner components will just cancel out. And the overall flux can actually be found by adding up all the flux on the little squares. And that way, the flux on some arbitrary boundary can be written as the flux through all of these little components of the boundary. And we can make those components small enough that we can use this trick. And so we can use this trick over the whole thing by adding up the gradients in each little small square, which is exactly what an area integral is anyways. Magic. And that is how Gauss's law works. You know, without that proof, it's sort of opaque, right? Like, why does this hold true? But like, once you see, like, do it across these little squares. Electric fields are vector fields. The electric force, right? That electric, well, it's not an electric force until you have a charge, but the electric field, well, it has a magnitude, right? And it has a direction. The electric field is the gradient of the voltage field. The electric field itself is a vector field. The voltage field is a scalar field. And it happens, more than happens, there's a good reason why. The electric field is the gradient field associated with the voltage field. And then this thing, we pronounce it grad sometimes, but its proper name for that little triangle there is nabla. Nabla dot f, that's the divergence. And that's, like I say, computed using that like sum of partial derivatives. And remember, in physics, the divergence of the electric field, where the physics comes in instead of math is where we say grad dot f, the divergence of the electric field, is equal to the charge density. Right? That's the physics. The physics is that on some level, what it means to be an electric charge is to be a thing which creates divergence in the electric field. Because the electric field is a field with zero divergence everywhere except where charge is. And when you learn the really advanced mathematics, you learn something called you learn about something called a Green's function, which is a function which has like zero, which has the property of basically having like some property zero everywhere, and then like infinitely having that property at one point. It has that singularity. And charges create, that radial charge. That's a Green's function for divergence. That's what it looks like to have divergence zero everywhere except one point where the divergence is really, 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 really big at an infinitely small little point, so that the integral of the divergence across this is like just the one of these points is 1, or whatever it ends up being. Those are that's how the physics ends up working out, is that each charge represents a certain amount of divergence in the electric field, which is a vector field, which has these vector field properties. And then that gives us the flux because of this little trick with little squares. Obviously, in 3 dimensions, you can't use squares, you got to use little cubes. But the idea is the same. You have your little cube, and you have the z face, the y face, and the x face, the same trick, except now the area is x times y, and that gets you the missing differential in the other directions. Same idea. But that's the idea. Charge creates divergence in the electric field, and then the integral of the divergence across a volume is the flux across the closed boundary of that volume. And so the integral of the electric flux over some boundary is exactly equal to the total contained charge, because the total contained charge happens to be the total contained divergence. Again, more than happens to be. There's good reason for that to be the case. But yeah, if anyone else has any questions or comments, happy to take them. But I'm sort of off the clock now, right? I run from 6 to 8, and it's 8. But I enjoy talking to folks. I enjoy doing all this physics, so I'm happy to take any further questions. No problem. And I'm actually about to stop the screen recording, so this is all going to go up onto YouTube. If any of you have a problem with that, I don't think you should, because like the chat shouldn't show up. But if you don't want the voice on the video, then I won't put it up. But otherwise, I can put it up. So I'm going to stop the video.